Okay, so now we're gonna get into actually like picking these components and then creating them in CAD. So how are you gonna pick which components you're using on your board, then how are you going to tell your CAD program what the parameters of this component are? So first of all, a few resources for looking for parts. DigiKey is like the #1 thing for electrical components. It's a huge catalog, well-defined search, very easy to find components. They have a huge selection and are generally the first step for finding electrical components. That's just kind of like my second resort personally. They have some electrical components. They also have a few things that you might not find on mouse, or like certain connectors, sorry, on DigiKey, like certain connectors, things like that. Yeah, I don't use these as often, but DigiKey is like definitely #1. And then yeah, Amazon has like, you know, kits of resistors. Like you want a resistor book with a ton of like 0805s of varying values. Amazon's pretty great for that. Since they have like very particular specialized parts. Yeah. Adafruit and SparkFun are two kind of like hobbyist resources. They have like existing modules for plug and play things. So if you need like a sensor or module, and they both have really great tutorials as well. These are kind of parts made by people who use these parts, hobbyists who are making projects. So it's really great, especially as you're getting started. We use these a lot for classes, like all the ECE project-based classes use these websites to find modules for robotics and that kind of thing. Okay, I went over resistors and capacitors with you guys. Those are, there's gonna be tons of those on every board. And the way that you're gonna define them, I mentioned this kind of in one of the videos, and I hope this didn't confuse anyone. I was talking about 0805s. The meaning of that is that these passes are often like denoted by this code that refers to the size of the part. So we were using 0805, these guys, on the board that I gave you. You can have much bigger ones. You can get huge. You can get really, really tiny. These are the smallest you're gonna see. These are like the smallest that I would suggest a beginner solder. I've used nothing smaller than 0402s. And bigger ones are good for like, power and that kind of thing. Like it's easier to dissipate more power across them because they're just bigger. So I'd recommend just starting with bigger components when you're first doing something and going from there. Don't try to make your very first board with 0402s, something like that. Yeah. Okay, surface mount technology versus through-hole. So that's if SMT refers to surface mount technology. And through-hole is kind of what it looks like. Yeah, it's a hole that goes through. And surface mount is just going to be not going all the way through. So surface mount components just sit on top of the board. They take up less space because you can run traces along the other side on the back of the board. Nice and easy to get assembled by a manufacturer because they use these like machines, which you'll learn about more later, to just pick and place the components onto it robotically, and it's pretty easy for them, pretty low cost, and yeah, really great for passive components like these resistors and capacitors. Through-hole has these leads that pierce through the board, so that's why they're going through. These are a lot easier to solder by hand, and they're more mechanically stable, so if there's any kind of stress or strain on these components, good to have it be a through-hole, like for connectors and that kind of thing that are going to be tugged on by people. Great to have through-hole. Ensures a really like strong connection because it's going all the way through and being soldered like on both sides. Whereas these are just kind of have a smaller connection, and it's like a little bit less stable. Good for heat dissipation because you have just more area. And like I mentioned, really great for connectors because they have like stress on them. So we talked earlier about different package types when we were talking about ICs. These are just a few of the many, 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 many types of packages that you will see when picking components. Some differences between them: you can have through-hole packages like SIP and DIP versus DIP versus like something like this, where the leads are supposed to be flat on the board, something like this. SOTs. Whether you have the leads on the inside or the outside. So for instance, QFP has the leads on the outside, but a QFN, which I don't believe is shown here, has the leads all tucked under the package. So it's a little harder to access. If you're soldering it by hand, it's pretty hard to solder one of those. So something where the leads are outside and accessible by your soldering iron is better if you're hand soldering it. Obviously, number of pins, you can have a 6-pin dip package or a 28-pin dip package. However, if you have, for instance, a 26-pin dip package or a 32-pin QFP, they're not all exactly the same size. They're going to have differences between just the overall size of the package, the spacing between the pins, the length of the pins. So don't just think, okay, I have a QFP package for 32 pins. That's all I need. You're going to need to look at the data sheet carefully and see what all those dimensions are. And we'll go through an example of this later in this. And often these packages, especially this more symmetric ones, have some kind of pin 1 marker for directionality. So you can see this little dot here defines where pin 1 is going to be, or this notch in this dip package. Just some examples. Okay, so how do you tell CAD what is going on? There are two files essentially that you will feed to CAD that will tell it what this component is, like what the heck's going on. And that's a symbol and a footprint. So a symbol is like the schematic, and the footprint is for layout. So a symbol is a logical connection of the component with like a representation. So this is a symbol. It's a connector. It's showing you it has these pins. These are what numbers they are, and this is how you connect to them. It's just that. It's very, very basic. And if you had a resistor, it'd be one side, other side, and then just a little resistor. That's it. Whereas the footprint is both a 2D and 3D model of what the component actually physically looks like, right? So this is what a connector looks like. You're telling it this is what it is. And you can get these CAD models. DigiKey has a lot of them, and manufacturers often provide CAD models for this purpose. And then you're telling it okay, when I put on the board, I need these pads for it to connect to. This is what you're going to solder to, and you need to tell it how big do you want those to be. They need to be able to fit the leads. These are the leads. You need to fit the leads through. You're going to need to be on both sides and be plated so it's connected. You're going to want a certain area of this is how big the part is, and don't put components underneath this part because it won't fit. So you're telling it all of those things, and we'll make these, and we'll get more into the details of this. So yeah, a symbol. A lot of components have existing symbols. You have a resistor, pin 1, pin 2, just both sides. Same thing with an LED. This is an LED because it's a diode, and this is showing that it's emitting light. For most ICs, it's just going to be a rectangle with pins, just like this. This could be a header, or it could be an IC. You don't know because it's just a symbol. And the pins refer to one input or one output of the device. So this is one pin. This is one pin. This is not a pin. This is just part of the drawing. So 2 pins here, and this has 6 pins. You want to check the data sheet for the pinout of the component. So that means you check the data sheet and it will tell you, okay, pin 1 is MISO, pin 2 is VCC, and so you can make sure that that's correct, because when you put the component in, it needs to match up. Importantly, a symbol does not need to be in order, because you'll tell, okay, this pin 1 is attached to MISO. You'll attach something to it, like a resistor or whatever, and that will logically connect it. And then when you define the footprint, you'll tell, okay, this is where pin 1 actually is. So this one doesn't need to be in order, for the record. However, footprint does need to be in order. So just to go over some terminology before I really explain this, layers in a PCB are just different physical layers. The board, you have copper and core material, and more copper and a solder mask. A stack up will show you what those layers are and the different materials that make up each layer. So whether that's copper or fiberglass, whatever the insulator is. So these are 2 examples of stack ups. This one is a 2-layer board. It only has 2 layers of copper, the bottom layer and the top layer. Whereas this one is going to have top layer, bottom layer, internal ground plane, internal power plane. So there's four layers. That's called a 4-layer board. You can go really high. You can go 16-layer boards, much more than that. But it gets pretty complicated. So probably starting off, you're going to have mainly 2, maybe 4-layer boards to start out with. So different kinds of layers. A mechanical layer is something that's physically a component body or an outline. Don't put things in here. A silkscreen is going to be the text that's printed onto boards. So if you have something that says R15 on these PCBs I gave you, that's the silkscreen. Paste is where solder paste will go for assembly, and solder paste is essentially it's like solder but kind of more liquidy, and that's what you put through an oven to cook the components onto there if you assemble at a manufacturer. We'll get into that more later, but that's the general idea. It's just where solder goes. Top, bottom layer, or like I mentioned in the previous slide, internal ground plane, power plane. Those are metal layers where traces are made. So that's where you connect things, where you draw wires are on those metal layers. The solder mask will cover all the exposed copper where you want it to be. So this is like, if you have a green board, that green stuff is the solder mask. It's covering the board and protecting any exposed copper from shorting or anything like that. So the word PTH, that means plated through hole. So that's like in this picture here, like this is a plated through hole. It's a hole all the way through, and it's plated, which means that it connects in the middle, as opposed to just a regular hole, which wouldn't connect the two sides. That's the difference. And a pad is like a chunk of copper, usually used for connecting a component. So so this is a pad. Okay, so footprint shows you where the pads are, where the holes are, and it indicates where pin 1 is and numbers all of them. So you can say, okay, that when I logically told you is connected to that resistor, that's that one. It's here. That's where it physically is. When I put this component in, I want this one to be physically connected to that resistor. And it gives like a clearance, like a little courtyard around the edge, of saying like don't put any components too close by because it won't fit here. There's already a component here. It gives you the outline, so like this is the range of where this component goes. When you're making components, you can either just make them completely by hand, like drawing each one of these things, or you can use something called like the wizard. It's like a little setup wizard, just like if you were installing a program, and that can like make components automatically for you. So if you have like a standard size of something, like an IC or something like that, like a FET, you can usually just auto generate those, and if you tell them like the rough dimensions, and it will like make a nice little model for you with the courtyard and with the keep out zone and all that kind of thing with a 3D model. The 3D body is like this model here that's like going into these pins. What will actually be on the board is like these little metal holes here in the silk screen, but what you will be putting into it is the 3D body. It's just a representation of what that component is. This is really useful for like showing height constraints and just visualizing what your board is actually going to look like. They're not technically required to design the board, but I find it difficult to look at a board and think, okay, so that's going to go there and that's going to go there. Just put them on. You'll see. You can see what it looks like. Yeah, these models, like I mentioned, are often available from suppliers directly, so you can just download a CAD model and import it directly. And again, I'll show you how to do that. Really, it's really useful to import these models also because let's say you messed up one of the spacings or did math wrong and your pins were spaced incorrectly. Importing this model and showing that it like fits into those holes shows you, okay, I did it correctly. This part is actually going to fit, and not getting to the stage of putting your board together and, oh shoot, I put these pins in the wrong spacing. So very useful. Now you have all these parts that you've made, whether via the wizard or manually, and you made the symbols and you've made the footprints. Like, how are you gonna keep these things together? Sometimes you just have like a library inside of a project where you'll just dump all your components and you copy and paste them from other libraries. If you have like an organization, like a product team or a company, sometimes you can keep a database of like parts that you have verified, like have correct models and that you've used and that you like, and then you can link to that database in Altium or whatever. Altium has this thing called a vault. I think it's actually called like an Explorer now in Altium 20, but it's like it's a vault of parts that other people have made and contributed, and those are not verified by anyone. I mean, maybe someone thought they were good, but they're often incorrect. They also often have problems. So don't just like pull something off the internet and trust it, because it can be wrong and it can majorly screw up your board. Once you make a part once, you want to either add it to a library or a database or something, so you don't have to keep remaking it every time you use a project. If you use Amiga 328p for 10 projects, you don't want to make this part 10 times. You'll see, like, making components is actually really annoying and takes a really long time. At some companies, there are like people called librarians that will make components for you, and that's like their job. At bigger companies, it's just really tedious and not that difficult. So yeah, you don't want to be making parts repeatedly. Okay, so grids. What grid is like just showing you like the spacing of things. So and this could be like a 1 centimeter grid, and this could be a 1 millimeter grid. For it's not, because this is like 5 times, but you can also have it in like imperial and metric. So this is just going to show you like where things are relative to the board. So you have a 10 centimeter board, here's each individual centimeter of it, that kind of thing. You're going to use this grid for parts, schematic, and layout. Your parts should be on a grid, your schematic should be on a grid, and your layout should be on a grid, so it's not just all like willy-nilly. It helps you like make and place things with a logical scale. So it shows you like, okay, I'm going to place these X length apart and not just kind of like freely place everything everywhere. And objects, like if you have a bigger grid on, they'll snap to the grid. So like let's say you place a component, it's going to put its origin like here. But if you have a smaller grid, you can put it here instead. With a bigger grid, you can only pick here, 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 here. The smaller grid, you can pick a bunch of different little spots. So it's better to place, bigger components on a bigger grid and then smaller components on a smaller grid, just for like logical layout. And the next part of this is going to be walking through a component creation in Altium. I'm going to do it manually because, and I think I'll show you both. I think I'll show you the wizard and a manual component creation, just so you know how to make components. It's not so scary because it can be kind of overwhelming. Like, how do I tell my CAD program what I'm making? And this is how. So yeah, we'll do that next.
Okay, so I'm going to walk through how to design parts in Altium. I'm going to do both, one using the wizard for a standard part, and then I'm going to do one manually with just this header here. So we'll start with the wizard. It might give you a better idea of how these things are made before jumping into completely doing it yourself. So I'm going to open up the Altium. And one way to do this is to create a schematic and a PCB library and then link them together and link the components together through that. So the first thing we're going to do is just define this part a little bit. So we're going to, I'm just going to call this part ATtiny85. This is just a microcontroller. It's not something that's used for your project. I was actually going to have you guys make the microcontroller used in this project as your, deliverable for learning how to make components in Altium. So we'll just double click this. And we're going to call it ATtiny85 designator. So we want to have this equal U question mark, or sorry, not equal, U question mark. And the reason for that is so U is just a designator for ICs. So there's different designators for different things, like R is resistor and C is capacitor, obviously, but then things like J is header. And that's just a standard, there's like a Wikipedia article that will list all these things for you, like crystal is X tall, but can sometimes also be Y. Yeah, there's a bunch of different things for that. And the question mark sets it so when you annotate this, when Altium assigns all the numbers for you, it will auto populate that with just the number that it is. So like if you had 3 resistors, it would auto populate them with R1, R2, R3. So that's why we leave the question mark there. This comment I usually set to the value, which is going to be one of our parameters, and then the description is given here. You can use either. Might as well just use the detailed one if it's not too long. It's always given on DigiKey. So that's that. We're going to add 3 parameters. So parameter. By the way, if you can't see this property window in panels, you can select properties, and yeah, that will show you this window. So we're going to have every part. I like to set 3 parameters, which is MPN for manufacturer, part number, manufacturer, and value. And this will basically just help anyone who's looking at your components like figure out, like they could find this part if they wanted to with the manufacturer, part number, and the manufacturer. So it's different from a DigiKey part number. So DigiKey is the supplier, the manufacturer is Microchip. So you could get these directly from Microchip, or get them through a third party like DigiKey. So we're gonna set that. Sometimes it adds sometimes it just adds like a space to the beginning. I don't know why it does that. Part number. This is the manufacturer part number. So you want to use that one, not the DigiKey part number. Just helpful for finding parts a little easier. You can probably find it either way. Okay, let's just put space. And then for the value, I usually just put like the part number, because this is what's going to be like written on the schematic, because I set this comment equal to value, and comment is visible. So that's what will show up under this part when you put it into a schematic. Okay, so that's it for setup, and then we're going to actually, draw the component, draw the symbol for it. So the first thing you're going to do is the P button is for place, and so you can, all the things that you want to do in a symbol are here. So rectangles and like arcs and drawing and that kind of thing, and pins, which are the things that you'll connect to. So we're going to start with just drawing an outline. You can change this at any point, so it doesn't really matter. Just draw a rectangle. You'll fix it later. And this part has 8 pins. So we're going to set 8 pins. And we're going to go to the data sheet and see what all those pins are and give them names. So here we're going to place, and then if you press P again, it's for pin. you'll see that there's like these little crosshairs. That is what your wires are going to attach to in your schematic, so they need to be facing outward. The way I just rotated that is by pressing the space bar twice. So space, 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 space. Make sure that that crosshair is facing outward so that things can connect to it on the schematic. And we'll renumber these later, so just place them, and then you can select just these guys, copy and paste, and again, make sure that these are facing the outside. So you want to spacebar, spacebar. Okay, now we have 8 pins, and the designator is like the number. So this is like 1, 2, 3, 4. That's the designator. So it tells you like actually what number it is, and that's going to be linked to the footprint. So it's really important that is correct. So 1 is a bunch of different things. You can label these whatever you like, whatever is easiest for you. It depends on what you're using them for. Like for instance, for this one, I'd probably call it reset because that's probably what I'd use that pin for. VCC is pretty straightforward and ground, but like things like this, what are you actually using these for? Are you going to connect a clock? If so, call it clock. X-tool. Are you going to connect just an ADC to it? You can use that, or you can just use the pin number if you're just going to be using it as a simple PIO input output. Same thing with like if you want to use like the SPI interface, you'd put like clock, MISO, MOSI, etc. But for now, I'll just call them all the digital pins what they are, except for reset. It's pretty important to remember which one is reset. But if you were designing a schematic with this, you'd look at this again. Just make it something that is clear what it is, and then when you're going through it, you'll know which one to connect to, and it won't be confusing. So let's start with that. So we're going to call this one reset, and this is a fun. See if I get this right. If you do slashes like this, it will, okay, I did the slashes the wrong way. It will give it, yeah, there we go. We'll give it a little hat. And that hat means active low. So we talked about this a little bit in the video, but active low means if you pull it low, that is when it is, for instance, here it would be like, that's when it's reset. One more, there we go. So this just means like, if you pull it low, this is active. So if you had some kind of pin that was, like an alert or an enable or something like that, and it had a bar on it, that means active low. So just so you know for the future. It's good to label things like that so it's super clear when someone is designing with it. We'll just call this, PV3. Oops. I believe this one was just ground. Yeah, ground, and then VCC. So important thing, see if this goes 1, 2, 3, 4, 5, 6, 7, 8 up this way. You cannot, in the symbol, it won't matter as much which ones you label them as, but if you do your footprint wrong, if you say like 1, 2, 3, 4, 5, 6, 7, 8, and so then VC is connected down here, like that will be physically wrong. So if you make this component wrong, you could potentially screw it up and like not have it wired right. I did that on the first version of one of these boards, so very possible, honestly very easy to do. So just keep an eye out for that. 6, 7, and 8 is VCC, which is power. The whole VCC versus VDD thing is a interesting battle between people with BJTs and FETs. Not going to get into it. It's weird. They mean the same thing. Drain versus collector. If you know anything about FETs and BJTs, just different kinds of transistors. Okay, so now we have all the pins labeled and they're correct. Each number is associated with what it actually is, and we have all the parameters for it. The last thing you're going to do is you're going to have to add a footprint, but we don't have a footprint yet. We're going to make that now. So we'll make a PCB library. This we're going to use the wizard for because it's a standard part, and I'll show you what that means. So if you go to Tools, IPC Compliant Footprint Wizard, it's going to give you a ton of options for different parts to make. And this is pretty interesting to look through if you're not familiar with package names. Like, what's a BGA look like? What's a DFN look like? What's some of these are really common things like QFN and QFP especially. Like those are really common packages for microcontrollers. You guys will probably be using a DIP, so we can just look through and like find which one it should be. This one. SOJ. Similar package. That's will work. Yeah, so there's just a bunch of different things you can look through. It's pretty cool to see the different packages. Anyways, today we're going to be using this ET Tiny, which is a, SOIC package, an 8-pin SOIC package. So now you've seen the pinout, you're gonna want to scroll to, it's usually the bottom of the data sheet is where like the package information is, and make sure you're looking at the right package. Where are you? Here we go. So this is obviously not the right package. There's a different number of pins, different kind of package. It's going to be this one. This is the SOIC. You can see that it looks like the right shape, 8 pins. So we're going to open up this in SOIC, small outline integrated package. And this, again, that's what it looks like, so you know that you're on the right page. And now you're going to go through this data sheet and first of all, I'll set it to 8 pins. And then we're going to go through and just check every single one of these and make sure that they're correct. Right now, they're not correct because your part's not going to look like that, right? I also like pressing this generate step model preview because it just makes like sexier looking ICs, personally. Okay, so this is a little tedious. And I mentioned earlier that this kind of thing is really tedious. I'm just gonna, I'm gonna open this in a different window. Just I'm going through it. Okay, so. So yeah, notice it's in millimeters. Important. You don't want to do it in inches and be wrong. So, okay, height. So the height here is referring to H, which is this. Oh, sorry. Width range is H. Of course, H is not height. So it's me this, and this is called E. That's why it's kind of important to like make sure you like know what it looks like on the package because they'll just call it different things. This one's just called E. So 5.79 to 6.2. Again, you can look at it in 3D and be like, okay, yeah, that looks more like this picture. That's more correct. We can move on. Thermal pad would be like if you want something underneath this, if like this component's gonna get kind of hot, like let's say it was like a regulator, the low efficiency regulator, or just a regular regulator, they all get kind of hot. You might want to put a thermal pad underneath it, and basically that will connect it to whatever plane is underneath it, and so connected to more metal just allows more heat to dissipate. We don't need that for this part, A, because it's not a real part that we're using, and B, microcontrollers hopefully are not getting that hot. The rest of them are just usually just like standard, you know, you just, yeah, it'll do this for you pretty correctly. If you want more precise things, you can like decide if you want like smaller pads. For instance, if your parts are commonly like shorting together, you might want to make the pad smaller, or if you're not really able to solder them to them well because the component totally covers them, make the pad a little bigger. But they usually calculates pretty good things for you. So we're just gonna finish that, and then we'll look at the part that is created. So if you want to switch between 2D mode and 3D mode, you literally press the buttons like 2 and 3 on your keyboard. So 2, 3, 2, 3. I don't know if it works on the number pad. No. Okay. So let's just go through this real quick and look at the layers and talk over it a bit. So to isolate a layer, you can press Shift S. You can press it twice and it'll completely isolate it, or just look at it more clearly so you can see like what's on each layer. They're also different colors, but sometimes it can be a little hard to just look at this whole thing and isolate the layer. So let's just do that. This is the top layer. Basically just means there's going to be like copper here. Nothing in the bottom layer. If you switch it to the bottom layer, you can do that. You can move components to the bottom layer, then this would just become the bottom layer. The 3D body is going to be on mechanical 13. Mechanical 15, this is a keep out. It's called a courtyard. And that's basically going to say like don't put components in this courtyard. Like keep this is my space. You know, if you have a resistor, don't put it like right up to here. Leave it outside of this box. Overlay is like the silk screen. So this is what's gonna be like printed onto the board. You can change this if you want. Like you can if you don't want this big pin, you can delete that. You can edit this whole thing if you want. This will just make it for you in the first place. And this is the pin 1 marker I was mentioning. So like you know, this is a symmetric part, right? Like look at this thing. Like the only thing that distinguishes it is this little dot, and so you have a matching dot on the board that will show you, okay, orient your chip this way. And that's helpful for if you're assembling it, and also if you're having a fab house assemble it. Nothing on the bottom overlay. Again, if you switch to the other side, this stuff will just move to this side. And then there's just going to be like paste, where they'd put solder paste, and where you'd put solder. And there's no hole, so the drill should have nothing on it. Yeah, so that's the layers for you. And if you look at it all together, now you can see, okay, there's a lot going on here, but that's what all those different things mean. It's not crazy confusing. So hopefully that was clear to you. Now you have this part. I would save these libraries somewhere, and then I would come in here and add footprint. And then you would just find the you'd find whatever library you called it and give it an associated footprint. So I would save this as AT-tiny85, and then I would define AT-tiny85 and say, okay, that's the footprint. And obviously this is not the right one, but and you need to make sure that that your pins are like correct. So like this is pin 1, and pin 1 needs to be reset. So if you were going through this and naming this yourself, see how this 1, 2, 3, 4, 5, 6, 7, 8. So if it auto-generated and said this is 5, 6, 7, 8, make sure you fix that, because that will again make it incorrect. Okay, so that's the wizard part of it. And we'll do next. We'll go through and do a manual one. Okay, so we're next going to make a part manually, so not using the wizard. And we're going to make this just a header. It's very simple. It'll be very quick. Okay, so you know how to make a schematic symbol for it already. It's exactly the same as this one. You know, you just make a square, name, give it 8 pins. The exact same way that you would make it the other way. The difference here we're going to do is making a component yourself. So you'll notice that this gave it a name automatically. You can change that to be at mega if you want, so it's more clear to you. But if you're making your own, you have to call it your own thing. So we're just going to call this 2x3 header. And the description is a through-hole 6-pin 2-row header. Okay. Now, I mentioned in the symbol, you can press P to place. Well, exactly the same in the footprint. So you can place, and the first thing we're going to do is place all the paths. So those are all the holes that are going to be needed to put this component in. So what this is going to need is 6 holes that are properly spaced, that you can stick this into, go all the way through, plated through holes, that you can put this component in, and then the 3D body to make sure it's correct. So first things first, you're going to place a pin in the origin. It's going to be pin number 1. These are multi-layered because again, you want to go all the way through the board. You want it to be a through hole. So make sure it's that, and then we're going to look at the data sheet again. So I press the data sheet, and it's right here. I'm going to keep getting in the way. Okay, this is the data sheet. Interesting thing about this data sheet is that it's not a data sheet for this exact part. It's a data sheet for any part of this type. So you could have like this. See, this has 12 pins. You might be wondering why. It's because this data sheet can be any number of these parts, which all have different number of pins. So 4 to 50 pins. So just showing you like how spaced they are and how tall they are, etc. But all we need in order to do this is the size and spacing of the holes. So we know that these holes are 0.9 plus or minus 0.5 in diameter, and this is in, I believe, millimeters. Yeah, these units are millimeters. So these are millimeters. So the maximum it's going to be is 0.95 millimeters. We want to give it a little bit of extra space, because if you make this exactly tight, you don't want to be like forcing this into the board. So we're going to just give it a little bit bigger. The range you can do this in is whatever's comfortable for you. And also remember, in manufacturing, the more holes you have that are the same size, the cheaper your board is going to be to manufacture. So if you have a different hole that's a similar size, maybe stick to that size. But for now, we'll just give it a little bit bigger than it currently is, maybe 1.1 millimeters, for instance. Yeah, let's do that. Okay, so now that we have this information from this data sheet, this one, we want it to be around 1. Let's just call it 1.1. Give it a 10%, 10-15% clearance, just so it's nice and easy to fit it in there, and you can fill it with solder. So this hole size is going to be 1.1 millimeter, and the outside rim is just like how much extra space you want on it. So you want a bit of copper surrounding it so you can solder to it. That's what those little like copper rings are around any component. So just make it a little bit bigger. You can kind of play around with it and see what you like. If this is too big, you can adjust it. I think that looks fine personally. If you're looking 3D, it's gonna look like that. I think that's appropriate. So and you can make them square or octagonal. It's kind of interesting. Cool. Okay, and then you can give it a tolerance. So you'd want to assign a tolerance here if you're manufacturing this, because you want your manufacturer to know like what is the appropriate amount of tolerance I can give this. But for now, we're just making these hobbyists, so just continue. You can copy and paste this. Copy and pasting, this is weird. When you copy, you get this. You have to press where you want to copy from, so the origin, and then you can paste, and you'll be pasting from the origin. Kind of wacky. Just wanted to let you know. So how you organize these pins doesn't really matter as much because you're going to be defining them. It's not like this part, you know, has some internal circuitry that you need to consider. It's just a header. It's just a pin that's going to connect one thing to another. So you can put this in whatever order you want. It's the exact same pin, but now we have to determine where it's going to be physically. So how far spaced apart they are. And how far spaced apart are they? Well, it looks like 2 millimeters this way, and I'm guessing the same amount this way. Yeah, 2 millimeters. So it's like square. So they're going to be 2 millimeters spaced apart. So we can call this -2. And we'll just do this again. Copy and paste. And this is going to be -4. And this is going to be -6. And make sure you give those the right designators. Is this a 6-pin or 8-pin? This was 8-pin. Ah, 6-pin, never mind. Okay, so we'll just delete that. There's no. This is going to be 3. And then we're going to take this, copy, and paste. And we're going to want this to, again, be 2 millimeters. You can actually select all of them and do this at the same time. So if you had more, do that. Okay, and let's give it the right part, the right designators. 5, 6. Okay, so I have this, and let's see if it's correct. Let's download so I downloaded this step file, which is like the CAD model, the 3D model. Open that up. And in Altium, what you'll do is you'll place and then 3D body. So if you want to like just draw a square, for instance, you could do extruded 3D body, and then you could draw, you know, like just like some kind of like, you could draw it yourself in CAD, but we're going to just import this model because that's what we know is correct. Things like, for instance, with the battery, I didn't have a model for that, so I just like gave it an extruded cylinder just to show the size of it and make sure that I don't have like CAD goggles when I'm working with just the pins of it. Anyways, we're going to go to 3D body, and I just download it here, just a step file, open it up, and then you'll place it, and we'll see what this looks like in 3D and make sure we did it correctly. But so it's just rotated. There we go. Okay. And you can basically just drag this into the right place. So it's currently covering all of our pins. Let's give it a little bit of an offset. This will just like push it up a little bit. There we go. And then we can kind of drag this so it's in the right holes. Maybe this hole's a little big. So as you can see, it's the right spacing. Again, where you exactly place it doesn't matter because we're just using it for CAD. Those holes do look a little bit big. No, I don't want to use sticky keys. So we could make it a little smaller. You know, you can go through a cyclic process here and adjust it. I'm not going to do that right now just because you can see, just make them smaller if you see something like this, or don't. You can solder those in, it's fine. So now it's nice that we can see that we actually made the pins in the right spacing. If we had done like, you know, if we read that wrong and thought it was 2 inches, then we would import this model and say, okay, well that doesn't fit. So just for instance, or 2 mils or something like that. So that's nice to see. And then, you know, we have our 3D body. Let's just go through and marking pin 1 here is less important for the part because you're not going to fry the part by putting it backwards, but it is important for, you know, if someone's plugging something in, maybe you want to just like indicate to them, okay, this is the corner, so you can just place a little arc, and I just place like a little dot on the silk screen just to show you pin 1. You can put it wherever you want. You can also give a courtyard, so that was on mechanical 15 earlier. I just did place, sorry. I just place an L's for line, and that will just create lines like this. So I don't know how far you want your courtyard to be out. And you'll just draw a square like that, and then you can, you know, if you want, like you can make it a little bit bigger. You can give this a little more berth. Yeah, a wide berth. Yeah, and you can give it like an origin if you want. You can draw. Sometimes they draw this on parts. They give a little like X marks the spot for like the center of the part. That's just useful sometimes. And yeah, so you can compare this to this component, and you might be wondering why there's no red for the top layer. You'll see these are through hole parts. They're on both the top and the bottom layer. So it's not red because they're just plated through holes. You can slide through to all these different things, and you can see that it's pretty similar. We can also apply like a solder paste to it if you wanted, or solder layer. But this is pretty sufficient for this part. So now if you want to look at it in 3D, it'll show you that. Yeah, it's kind of hard to see because it's white, but it's this little dot here. That's the pin 1 marker, and that's it. Now you have your own part, and you can put this in. You can link it with the schematic. You make a part through it, link the footprint, and then you can put it into your schematics. So that's it. It's a little annoying to do this. I know, like you might have seen this video took however long. It's really tedious to make your own parts. It's very annoying. So that's why you should try to use the same parts when you can, and make them right the first time so you don't have to edit them. You can also pull parts off of the internet, but make sure that you check them and then edit them if they're incorrect, because you do not want to have incorrect parts on your board. Manufacture the board, get it back a week later and realize, oh shoot, the person who designed this, didn't space these pins correctly or numbered them incorrectly, or something was wrong with it, and your board's not going to work now. You can't put that part in there. So to make sure you check things if you find them on the internet, and really just try to make your own components is like the best practice. So so that's that. I'm gonna have you guys make the mega part. I'll post more information about that, but essentially I want you guys to do a similar thing that I did with this component. You can either make it by hand or make it with the wizard. And I want you to make the AtMega 328P, which I will give you guys a datasheet for and a link to on DigiKey for all that information. And I'll have you submit that to like a drive folder just for me to check over it and make sure you're not missing anything important. So yeah, good luck with that, and I'll talk to you guys later.